Hello, I'm really delighted to join you today to talk about sleep disorders and how they relate to aniridia. I thought I'd divide the presentation into three component parts: an introduction and background into sleep and circadian rhythms. What happens when these systems fall apart and one acquires sleep and circadian rhythm disruption, or SCARD, and then sort of a leap to the future and some hope, which is how can we find ways for correcting SCARD? Let's kick off with the introduction and the background. And really, I want to frame what I have to say with this in mind. This is a couple of responses to questions I asked a mother with a child with congenital aniridia. My first question was, what impact does John's sleep, and this is not the real name of the child, what impact does John's sleep disruption have on your sleep and other family members? And how does this affect your ability to cope? Mother's response was, at times, it has affected us greatly. If John is having an episode of poor sleep, it normally means frequent wakings or not sleeping at all. This means we are all kept awake. I would say this has caused myself to nearly become completely burnt out at times. And my second question was, how important would it be for you if there was some way to correct the sleep-wake problems of your child? And the response was massively important. It has such an impact on all of the household. Also for John, the lack of sleep on top of his sensory fatigue causes huge issues for him. I think if we could correct his sleep, he would find his school life much easier. And so I think with that in mind, let's now look at the biology of sleep. So this is an image of the brain, and if we look a bit closer into the hypothalamus, deep within the brain, we see a structure called the suprachiasmatic nuclei, which sit either side of the third ventricle, above the optic chiasm. Now, this is the master clock. It comprises about 50,000 cells, and each of those cells can tick. It has its own biological clock, which, working together, as I say, perform this master clock, this key regulator of our 24-hour rhythms in physiology and behavior. This internal clock is of no use unless it's set to the external world, and for that we need our eyes. And our eyes detect the light-dark cycle, and this is an image of the retina, and these are the rod and cone cells. But what we discovered is that it's not these cells that are required for the detection of the light-dark cycle to set the internal clock to the external world. If you have no rods and cones, you can still regulate the clock to the light-dark cycle. And that's because there's a third receptor system called photosensitive retinal ganglion cells that are detecting this light. So we have light detected by the eye and those photosensitive retinal ganglion cells. And a key point to make is that the circadian system needs a lot of light around dawn and dusk. So bright light of at least 30 minutes. So I put 100 to 1,000 lux here. Average office lighting or home lighting conditions would be 1, 2, 300 lux. So we're talking the sort of light that you would see outside, and not just a flash of light, but it needs to be sustained exposure for 30 minutes or more. Okay, so this light-dark message is getting to the clock. The clock is then sending out messages to the rest of the body. And in fact, each cell in the body has its own circadian rhythm, its own ability to generate a 24-hour oscillation. And it's those cells in their organ systems that are driving rhythmic physiology. So we see here the profile of melatonin, and we'll come back to melatonin shortly, the hormone testosterone, cortisol, the stress hormone rising in anticipation of waking up, the temperature cycle, growth hormone, and indeed the brain's ability to process information drops to a pretty poor performance in the early hours of morning, but then rises in anticipation of activity and the day. Now, the most obvious of our 24-hour patterns, of course, is the sleep-wake cycle, as we see illustrated here. And the sleep drive is low during the day, but of course high at night. And the key thing is, how do we generate this flip-flop from the sleep state to the wake state? And you can think of it as a bit like a seesaw. How do we go from wake to sleep? And the first point to make is sleep is an interaction of all of the key neurotransmitter systems within the brain. So they're illustrated here, and a further interaction with multiple brain structures. So we see the hindbrain, the midbrain, the cortex, the hypothalamus, all interacting to generate that states of sleep and consciousness. And of course, part of that within the sleep system is the REM, non-REM cycle. That's great. But how do we time all of this? No surprise, we have the circadian system, the master biological clock within the brain, the suprachiasmatic nuclei, time stamping everything. But there's another timer, and it's called the sleep pressure or the homeostatic drive. It's the most intuitive part of sleep. The greater you've been, the longer you've been awake, the greater the buildup of sleep pressure and the greater the need for sleep. And of course, in our society, there's a third factor that will influence sleep, which is our stress, anxiety, and our mental health status, such as depression. Let's just examine the interaction between the clock and the sleep pressure in a bit more detail. So here we have a diagram of the wake and the sleep cycle. And what I want to talk about first is sleep pressure. So from the morning, as we're awake, the sleep pressure rises. But when we're asleep, the sleep pressure dissipates. Interestingly, sleep pressure is highest obviously just before we go to sleep, but it's really high in the afternoon. And we don't necessarily fall asleep at that time, or hopefully not, because of the action of the circadian system, which is providing a drive for wakefulness. So the drive for wakefulness exceeds the sleep pressure as we go through the day. And in fact, ironically, the wakefulness drive is highest just before we go to sleep. The wakefulness drive from the clock then declines. This allows us to fall asleep. And then during sleep, the wakefulness drive is low. And then as we approach morning and wake up time, we have an increase in the wakefulness drive, leading to a wake up. So these are really important factors that interact to time our sleep. And if these become disrupted, then sleep timing can be completely fragmented. Okay, I haven't talked about melatonin in this process, and some of you will be asking, what is melatonin? Isn't it the sleep hormone? And it's very confusingly called the sleep hormone, and it's really misleading. It is absolutely not a sleep hormone. Melatonin is released from the pineal, peaking in the blood around 2 o'clock to 4 o'clock in the morning, and then it declines around dawn. And this is true for both day active and night active animals. So mice, for example, have high levels of melatonin at night when they're awake. So it is clearly not a universal sleep hormone. Individuals who do not produce melatonin, and that's been demonstrated in tetraplegic individuals, or indeed people on beta blockers, of course, very many people, and they show a greater than 80% reduction in melatonin production from the pineal. But sleep continues with only very minor changes, again indicating that melatonin is not a sleep hormone. Melatonin supplementation, so taking a melatonin a tablet, say 3 milligrams an hour or so before bedtime, and this has been shown to increase total sleep time by a maximum of 30 minutes a night, and it reduces the time it takes to get to sleep. So sleep latency is reduced by around 10 to 15 minutes. So clearly it's having some effect, but it's a mild effect. So melatonin seems to have a small direct action to promote sleep, and or it provides an additional signal to tell the brain that it's nighttime. And interestingly, although melatonin is suggested as a supplement in aniridia, no trials on melatonin supplementation have ever been undertaken. Okay, so what does sleep provide us? We can think of sleep as providing an opportunity to rebuild our energy reserves. It rebuilds our metabolic pathways. It can be useful in removing toxins and harmful waste while we're asleep, and it coordinates growth and repair. And in terms of brain function, sleep allows us to develop our memories. It also processes our emotional and cognitive signals. So, for example, the tired brain tends to remember negative experiences, but forget the positive ones, which is very interesting. And also it allows problem solving. So if you want to come up with innovative solutions to complex problems, a night of sleep has been shown hugely to increase your ability to do that. So the quality of our sleep defines the quality of our wake. So what happens when we don't get enough sleep or sleep is disrupted? So sleep and circadian rhythm disruption. What I've sort of illustrated here is immense complexity. You've got all those different bits of the brain interacting, all those neurotransmitters. You've got the influence of sleep pressure, the circadian drive, light exposure, of course, has to be right, and there can be the additional problems of stress, anxiety, and mental health status. And what this means is that the complexity of generating the sleep-wake cycle makes it very vulnerable to disruption. And the sort of disruption that you see can be divided into three domains. If we look at the emotional responses, we see the impact of SCARD will increase fluctuations in mood, increased irritability, anxiety, loss of empathy, the failure to pick up the social signals from others, increased frustration, risk-taking impulsivity, negative salience, that negative view of the world, increased desire to take stimulants such as caffeine during the day, and then sedatives at night, and indeed in some quarters illegal drug use. If we look at the impact of SCARD on our cognitive responses, our cognitive performance is impaired, our ability to multitask is certainly impaired, poor memory consolidation, poor attention, poor concentration, poor communication, decision making is impaired, creativity and productivity takes a hit, our motor performance and indeed our social connectivity are all impaired. And longer term, the impact on physiology and health can be quite dramatic. So, of course, at the mild end of the spectrum, we have daytime sleepiness and microsleeps, this uncontrollable need to sleep. But long-term SCARD has been shown to predispose to cardiovascular disease, altered stress responses, altered sensory thresholds, infection and lowered immunity, which probably accounts for the higher rates of cancer, metabolic syndrome, type 2 diabetes and obesity. Respiratory diseases such as obstructive sleep apnea and asthma are increased by SCARD, and of course depression and psychosis are a very common consequence of sleep and circadian rhythm disruption. So sleep and circadian rhythm disruption is not simply the inconvenience of feeling tired at the wrong time. It's associated with emotional, cognitive, and long-term impacts upon physiology and health. So what can we do to correct sleep and circadian rhythm disruption? What can we do? We're using in Oxford our knowledge of how circadian rhythms of sleep are regulated and generated to correct SCARD. And the first thing I should say that SCARD disruption isn't just one thing, it's really complicated with multiple causes. And I hope the next slide illustrates that. So this is the sort of really introduction into the next slide, which is a cartoon of essentially several days. And what we see here is sleep represented as a black bar, a horizontal black bar each night. So we see that during the night and during the week, sleep occurs roughly at 10 o'clock to 6 o'clock. This is a cartoon. There'll be lots of individual variability. At the weekend, then sleep might be slightly delayed and wake times might be slightly delayed as well. Then back to the work schedule of a stable sleep-wake, weekend again, and then back to the work schedule. What I'm now going to show you are different sleep patterns based upon this cartoon I've just illustrated. So here we see the first one is normal sleep, which is what I've just shown you, and the circadian pattern would look something like this. With the timing of the circadian oscillation occurring at the same time each day. And as I say, that's what we see in healthy adults. Advanced sleep, where individuals are going to bed early and getting up early, where we see, no surprise, an advance in the circadian oscillation. And this is seen in genetic conditions such as advanced sleep phase disorder, but also in aged adults. Delayed sleep is where you're going to bed late and given the opportunity, getting up late with a delay in the circadian oscillation. And we see this in another genetic condition called delayed sleep phase disorder, characteristic of adolescence, very prevalent in depression and psychosis, and also in neurodevelopmental disorders. And there are papers on delayed sleep in aniridia, of course. Free running is where essentially the clock is not connected to the outside world. It keeps on ticking, but it drifts through time. And so the clock will get later and later and later each day for most of us. You see this, of course, with no eyes, severe eye loss or eye damage, no exposure or not enough exposure to natural light, depression and psychosis, neurodevelopmental disorders, and neurodegenerative disease. Insomnia is essentially not getting to sleep at the desired time, waking up, and then daytime sleepiness. And this is associated with a depression, with a lowered amplitude of the circadian oscillation and a variable phase, a variable timing of that oscillation. Again, seen in aged adults, dementia, neurodevelopmental disorders, depression, psychosis, metabolic syndrome, and neurodegenerative diseases. And then finally, essentially no rhythmicity at all, arrhythmicity, where the circadian oscillation is flattened and there's essentially no specific timing. It's completely arrhythmic. Again, seen in severe dementia, severe neurodevelopmental disorders, severe depression and psychosis, severe metabolic syndrome, and severe neurodegenerative diseases. And as many of you will have experienced, aniridia is associated with delayed sleep, free running sleep, forms of insomnia, and indeed completely fragmented sleep. Okay, so what can we do? Let's get into the sort of mechanisms, and let's first of all just briefly introduce the clock. I said that the individual cells can generate a circadian rhythm, and it's based upon genes which produce proteins, and those proteins then turn off those genes. And what that leads to is an oscillation of the sort I've just illustrated. Okay, so where we are at the moment is we've understood very much how light is picked up by those extraordinary photosensitive retinal ganglion cells, and we've worked out the neurotransmitter release patterns and how those neurotransmitter release patterns give rise to a signaling cascade, which then can enter the molecular clockwork and change the timing of the clock. It can change the timing of the clock, or it can change the amplitude of the clock. And so it's that basic biology that we've been able to dissect. And where we are at the moment, and I should declare a declaration of interests, because three of us, myself, Arti Jagannath, and Sri Vasudevan, have developed a spin-out called Circadian Therapeutics, which has been funded by Oxford Science Innovation to try and develop drugs which will correct those circadian rhythm disorders that we talked about earlier. So where I'm going with this is that we want to replace light with a drug that will essentially trigger the same signaling cascade that light will trigger, and that will interact with the molecular clockwork and change the clock. Okay, this is an example of one of the drugs we've been working on, and it's going to start in human trials later this year, but the data I'm going to show are from a mouse. And what we see is a shift in the clock on this axis here. So 0, -1, -2, -3. The greater the shift of the clock will be indicated on this axis here. And we're looking at a vehicle which is basically a saline, and you see this is the data here which has been normalized to 0. We'll expose the mouse to light, and of course this produces a big shift in the clock. This is highly significant from the vehicle, no great surprise here. But the drug that we've been working on is called CT1500. The blue bar here shows that CT1500 produces an effect which is not significant from light, i.e. it's the same as light, and of course highly significant from the controls. And so here we have a drug that is mimicking the effects of light on the clockwork. Now, the only FDA-approved drug that's been approved for use for non-24-hour sleep-wake disorders is a compound called tazimultion. And what we decided to do was compare CT1500 and light with tazimultion. And we were really rather surprised by these data because they were not significantly different from the control, although there was a trend. And we went back to the literature and we read that tazimultion, or Hetlioz as it's sometimes called, had a significant effect on subjective sleep in only 8 out of 40 individuals, 20% of the experimental group, who showed some self-reported sleep. And it's really interesting because it goes back to my point about melatonin. The tazimultion is based upon stimulating the melatonin pathway. And as I said earlier, melatonin is a mild modulator of sleep, which presumably explains why tazimultion has very little effect in regulating the sleep-wake timing. Okay, we're starting our clinical trials in collaboration with Blind Veterans UK next year, after we've done the first in human trials later this year. So hopefully we'll have a drug that can fully mimic the effects of light on the clock and then stabilize the sleep-wake patterns of these individuals who have lost their eyes or have suffered radical eye damage. So we're really excited that we can find now a biological replacement of light and give back a sense of biological time to these extraordinary individuals and then other patient groups as we go forward. Where we are at the moment is, I've just told you about one of our drugs, CT1500, which mimics the effects of light on the clock and can be used for free running or drifting rhythms. We have another drug called CT2500, which can advance the clock in delayed sleep phase disorders. Another drug called CT2600, which can enhance the effects of light on the clock, make the clock more robust and reduce the fragmentation of the sleep-wake cycle. And then finally, for those non-24-hour sleep rhythms we discussed, we've just sort of discovered this extraordinary compound, CT3500, which can actually increase the amplitude of the clock and restore circadian rhythms where they're otherwise massively fragmented. So I think we're at a very exciting stage. Finally, we'll have some weapons in our toolbox to try and restore sleep-wake disruption across the health spectrum, and particularly relating to delayed sleep, free running sleep, insomnia, and fragmented sleep, which are, of course, some of the conditions experienced by individuals with aniridia. Okay, so what I'd hope to do is provide you with some background about the biology of circadian rhythms and sleep. Then the point of the second point, which is the impact of SCARD, really demonstrating that sleep disruption is so much more than just tiredness at the wrong time, but has major impacts upon our emotions, our cognition, and indeed our physical health. And then sort of a good news story, I think, using our fundamental understanding of how sleep and circadian rhythms are regulated and to some extent generated, we can develop new drugs for the first time that will correct sleep-wake deficits across many different groups, but hopefully for aniridia in the coming years. And I leave with this slide, which is the blind sleep study for those individuals with blindness and partially sighted individuals who'd like to take part in a sleep-wake study. The details are illustrated on this slide, and I will leave this up for your consideration. And if you'd like to join this study, either check us out on the website or send an email as indicated here, or indeed use the telephone link and leave your name and number and we'll get back to you. Okay, with that I'll finish, and I'm delighted to take your questions. Thanks very much indeed.